Hello and welcome to Structural Geology 101. Throughout this course we're going to try and cover all the various aspects that comprise structure in geology. And structure itself is a very broad term. It can refer to the most minute microscopic textures in a rock all the way up to the most megascopic regional geometry and morphology. We're going to try and separate it and understand the various stress-strain relationships, which are some of the most important parts of structure because they define how things got to be how they are, and they define the history of a rock, the kinetic history of a rock, which can often answer a lot of important questions. So we're going to start with primary structures. These are structures that are acquired during the genesis of a rock, its original texture, for instance, when a magma freezes, or the original bedded content of a sedimentary rock, the original orientation, the original lineations that happen when magma flows or foliates. So we'll talk about primary structures. There are also non-tectonic structures. Now, in a broad sense, almost every structure that we see is in some distant way, at least, due to tectonic forces. But to simplify and to kind of give categories to what we're doing, we're going to call them non-tectonic structures if they're sufficiently removed from plate activity so that they don't seem like a direct tectonic structure. Now, one of the most important subjects that we're going to cover in later lessons will be stress and strain relationships, because structures are generally caused by stresses and strains. Gravity, tectonic, overburden. There's all sorts of ways to qualitatively discuss this, but we are going to want to quantitatively discuss it in the future because very important interpretations can be made based on the past strain of a rock. So let's get going, let's get started. First we're going to talk about some basic terminology and structures that we're going to see. Of course, there's bedding, and everybody's pretty familiar with that. That's just the original horizontal layers that are laid down in deposition, and the bedding is defined as the planes that are parallel to that. And we have cross bedding, and cross bedding is a very important thing to recognize in rock. It can indicate paleocurrents, it can indicate the wind in the past. This is a dune feature, a riverbed feature. They can often look very complex and be a little harder to identify, but there can also be very important facing indicators so that you can tell which side is up. We're going to talk about compaction, and that's something that's due generally to gravity, to tectonic forces. It's a type of compression. And we'll see overturned bed. It's important to recognize that beds are not always in their, or well, not always apparent in their order, because so much tectonic activity has gone on in the past that oftentimes they can be completely overturned. Strata is a word we're going to be using a lot, and stratigraphic facing, which is also known as the Younging direction. That's how we describe in which direction a set of beds gets younger. And you can see in some of the pictures here some of the illustrations of what I'm talking about. Now, cross bedding being so important, let's take an extra minute or two to talk about that. When air or water moves under some sandy depositional environment, like we said, dunes in the desert, or little sand that's running along the bottom of a riverbed, the grains build up into dunes or piles. And when the sediment piles reach a height where they are no longer stable, so you can kind of see in this little picture I've drawn up here, which is what defines the angle of repose, the height at which they're no longer stable. Those grains avalanche down the side of the pile, and they stack up in thin depositional layers at an angle. So you can see by the illustration here why they indicate the direction of the current or the wind at the time. So over time, multiple avalanching episodes are going to give you all these thin layers, and those are called cross-bedded laminae. Now, as with anything else that falls downhill, there's kind of a zone of runout at the bottom. You can see up here. The grains don't just roll to the base of the bed and then stop immediately like it looks like in this picture here. There's going to be grains down here stacking up. And this makes kind of a tail uh, to the cross-bedded laminae, and it lays on top of the bottom bedding surface, and that is what helps us to determine the stratigraphic up when we're looking at cross-bedding. So it can be a little complicated, you're going to have to look closely, but there are these features in the structure that's going to let you know which side is up. Now, the top of this cross-bedded structure is not usually preserved because the movement of grains across the top, the wind, the current, exposure usually erode the top away. So you have a common morphology of these incomplete crossbeds. So you need to get used to looking at them and recognizing them. And often you're going to have a lot of different currents over the same area in the same riverbed. As the river changes its course a little bit with weather, with season, with its momentum. So you're going to look for lots of layers of crossbedding that can look very chaotic until you can recognize them and place them. And obviously you're going to see a lot of confusion, for instance, in dune fields, because that's dependent on the wind, and so that is definitely going to see some major seasonal changes. Okay, so that's some of cross-bedding, and of course we're going to talk more about this in the future, but that gives us an introduction. Now, we're going to go into some sedimentary structures and talk about some terminology that we use often here. There's grading, and grading is the separation of sizes of grains. You remember sorting. Is it poorly sorted? Is it well sorted? Well, a graded bed has got you can see the little illustration I've got here, it's got the grain sizes separated. And this becomes very important because there are some very important graded sequences that help us to recognize certain environments. For instance, a turbidity flow. And you can see a little illustration up here about how a turbidity flow works. You've got a whole bunch of sediment just waiting to drop into, say, a marine environment. You've got a mountainous coastal environment, and let's say there's a storm or an avalanche caused by a storm. There's some kind of disturbance, and you have all this sediment here flowing off the mountains or avalanching down this continental slope. Let's say that this is sea level here. And as it comes down, you've got the dense stuff coming down here, and on the, you've got the gentle slope down there before you get down to the marine floor. A lot of it is going to be stopped there, but then there is a sort of less dense cloud of debris and crud that just keeps on going. And as it flows down here, what's going to happen in the water? You're going to have a separation. Your heaviest, biggest grains are going to settle down first because they're never going far from the ocean floor. They're not floating. But then you've got a ton of floating crap, and as everything settles down, it's going to settle out. And you've got the Newtonian laws of gravity. Your heaviest ones are going to settle first, your finest ones last, and you get a turbidite, which is also defined by the Burma sequence. It's a very specific set of layers that you expect to find in a turbidite deposit. And these become important because turbidites can be huge events. And here's your Burma sequence. You've got this scarred base with tool marks, and it's going to have tool marks because you've had this big event take place over it. You've got massive sand and granules down here. You have cross-laminated sands here with your little bit of a current going on, your laminated silts, and then your pelagic mud, because that is the last stuff to settle out of the Malay. So we've got some important sedimentary structures there, and let's go to our next slide and we'll talk about some surface markings that you can expect to recognize. And none of these are quite as obvious as they might seem in a cartoon, so obviously you need to get used to looking at real rocks that have these, but all of these can be facing indicators. They can help you understand the environment you're dealing with. So they're important things to be able to put together when you're going to make geologic interpretations or predictions. You've got animal tracks, obviously, and we don't have to go too much into that. There's a whole lot of kinds of animal tracks, but they can often be confusing and a little harder to define than you might think. Now you have classed imbrications, and this is a shingle-like stacking of your clay flakes, your pebbles, your platy objects, your clasts. Now, this usually happens under the influence of current. You can also have gravity-driven imbrication, like clay flakes in a shale. This orientation in a current is achieved to minimize the pressure exerted on the clast under flow. So that is why they arrange themselves. And you can see in this little illustration here, we have a clast supported imbrication, we have imbrication in matrix. This is kind of the way that your current is going when it creates this imbrication. So you can start to recognize what that is, what that word means, and later on you'll start to be able to put these things together and build a story for where your rock has been and what it's done. And you've got flute casts. Flute casts are interesting. They're little asymmetric troughs formed when your vortices or mini tornadoes in your riverbeds dig into the unconsolidated substrate. They're not very big. You can recognize which way your current was going because they're shallower and wider at the downstream end because the tornado is dying out downstream as it moves forward, and so it's kind of widening and shallowing, losing its directed force. These are facing indicators as well, and they can establish your younging direction, like we talked about. Which way is your set of beds getting younger? You've got mud cracks, and those are pretty self-explanatory. They happen when the mud dries out. You have raindrop impressions. You have ripple marks. Ripple marks can be a little confusing for somebody who hasn't seen them before because they look a little strange from certain angles. You've got the pictures here of how they can look, and I think we've all probably seen some of those at this point. And then you can see here a little cross section of your ripple marks and how it happens. You've got your current coming in here, and it creates this little whirl about, and so it digs out a trough. And that's how you get your ripple marks going. So it's helpful to you if you can picture how these things are formed. Then you have your traction lineations. These are usually very small. They're trails of sediment that's either accumulated in the wake of larger pebbles as the current pushes them down, or they're just debris being dragged along a riverbed that leaves little lineations. And often they're just very subtle lines formed in the riverbed due to the alignment of inequal grains. You know how we talked about imbrication that reduces the pressure that's being felt on the clast as the current goes past it. Well, grains also align to do the same thing. Obviously, if you are perpendicular to the current, you're going to experience a lot more resistance, so you're going to want to run parallel to the current. So that can also be a traction lineation.